Greetings. Here's a box that had a PCB in it. See if you can guess who made this. And I'm going to leave this on for a while, but if you need more time, you can pause the video and look for clues. Anyway, suspense. It's an Intel system design kit. It's the SDK 85 system design kit, and the right side of the board has a selection of Intel chips centering around an 8085 processor, and the left side, from here on to the left, was a rather large prototyping area which one of the former owners decided or wasn't shy about using. We're going to talk about this towards the end of the video, but really our main focus is this side of the board. I got this off eBay pretty reasonably because normally anything that says Intel and implies vintage Intel is not cheap to get. But I guess this one, nobody knew what this was, or it didn't look exciting, and thus I got it because it's essentially an 8085 trainer, minus the prototype area, of course, and it came as a kit that you had to put together. It came with everything, even with full sockets, and it taught you how to use an 8085. It came with the box I showed you before, also with the original 8085 manual, but really no instructions for this board, but thank the universe for the internet, because a scan of the manual was provided, and since I like hard copies of stuff, I printed and bound it, so I know what I was doing and how to demonstrate it. When I got this, it didn't work. I hooked up 5 volts to it. It has an input for plus 5 volts and a minus 10 volt input, but the minus 10 input is only used if you are going to hook this up to an RS-232C terminal. No, an RS-232 terminal, actually, because that gives you the plus minus 5, or it derives the voltages that it needs for true RS-232. But I hooked up 5 volts to it. I checked the 5 volts on the boards, but nothing happened. So after diagnosing this, it turned out that the CPU was dead. The 8085 over here was not working. So I went through my parts bin. I had one that was second sourced by Toshiba, and it did this. It works. Bad processor. And it's kind of ironic that I have a second source CPU in here. Everything else is original Intel, which was their purpose, to get people who use this to just borrow this design and put it into their product, and thus buy everything from Intel. On a quick look, you can see there is no apparent RAM or ROM on here. Of course there is, it's hidden in here somewhere, but the traditional RAM or ROM were not used here because these were the chips they were trying to push. This was supplied as a kit that you had to put together yourself, of course, and saved some labor on that and made it that much more interesting. Ooh, it's a kit, you build it yourself. But once you put it together, hopefully you hit power and this would come up, and that would mean it's all working. So let's go over the Intel portion of it and see what all of these chips are. So at the center of it all is the 8085 CPU, which the original one in there was non-functional. It's kind of ironic to end up with the second source one here, as I said before, but if you believe what they say in books and unauthorized histories of Intel and stuff, Intel invented this. Intel built it. Intel came up with it. They get all the credit for bringing this into existence. But it is said that their chip yield was not very good in the beginning. When they were making this, it was around 60%. Chip yield being when they made a bunch of chips, how many of them worked, and 60% of them worked. The Japanese second sourced it. They didn't invent anything other than quality control. It is rumored that the Japanese equivalent of the 8085 had a chip yield of 85% and up. So we invented it all here, but the Japanese invented the proper manufacturing procedures to make them financially viable. But anyway, so that's the CPU over here. Right under the CPU, we have the Intel the 8355, and that contains the ROM that has the system monitor in it, and it has a bunch of I/O ports. This guy is an 8155. This has the RAM in it, and also I/O ports, which all end up over here on these connectors or holes here, so you can do your own neat stuff in the prototype area. The last 40-pin chip is an 8279 keyboard display interface with an associated shift register here, 74 LS156, and that allows the processor to read the keys and to display. This is a 6-digit display, 6 digits here, space, and 2 digits, which is kind of a common setup. The Heathkit 3400 also had a 6-digit display, because generally what you do is you display a 16-bit address or a 4-digit hex address on the left, and the contents or the byte on the right. Other than that, what we have, well, we already talked about the 156. That's an off-the-shelf thing, and it does not say Intel on it. But we also have a 8205 address decoder here. That is an Intel part, which I think is functionally equivalent to a 74138, but it probably has a different pinout. But as I said before, they rightfully tried to push their own parts. So with all of that said, we now know what this part, what the heart of this does. So we can have a look now at the monitor and the keyboard. The monitor lets you interact with the processor, or tell the processor what to do, of course. And we have purpose. I mean, the keys are basically, we have these 8 keys over here that are specific commands, and then we have a hex keypad that also has a second function. And if we look at this, these are the registers of the 8085, and stack pointer high and low, program counter high and low, and then registers HL, A, B, C, D, E, and F. So logically, the very first command we should try is to display the registers. Now, another thing that this needed fixing was the keys did not work very well. They worked, but essentially it's a keycap, and underneath it is a spring and a copper contact. The contacts were pretty corroded, so they were not working or they were bouncing horrendously. So the keycaps came off real easy. Just sprayed it with contact cleaner, let it sit for a few hours, and that seems to have fixed it all. There's still some key bounce in here, but nothing too bad. So anyway, back to the command. It's the examine register, and it gives you that prompt. And now you can use just the keys to show you the contents of the register. So if we start with an H, it says that register H has a hex 94 in it. Using the next key, it'll step through all of the other registers. And I guess that's the end of it. So we have to hit it again to see like the remaining registers. No, that's not right. I was actually entering stuff. I forgot to hit the next key. So what we do need to say is examine register. That key bounces. We say A, contents A. Now if I just typed another number in, it would alter the contents of register A. So now to just examine, I have to hit next, and it'll go through the remaining registers. Other than that, then the biggie is substitute memory, which is this one. So what you do is you type in a memory address. Let's see. Hit next, and then you can alter the contents of it by typing in a new value. And then when you hit next, it enters that value and goes to the next memory address. So you already know what's coming here. No mnemonic assembly language here. You got to hand assemble everything you want to put in. Write the opcodes next to the to whatever you've handwritten in assembly, and thus you load the program. Now, when you hit reset, the manual states that it does not stomp on memory. So even though you hit reset, it goes back to the sign-up screen, memory is still left intact. However, when you turn power off, nothing is left intact. There's no backup, there's no battery on here or anything like that. But it would probably be cool to enter a short program and make it do something. So a short program I found was the 4-digit hex counter. I mean, add 2 numbers in hex notation. It's not that exciting, but a 4-digit hex counter should be really exciting. And as I mentioned, it gives you, the first column shows what address in memory you enter the code into. This is the actual hex code you need to enter, but they do show you the mnemonic, the symbolic, what you would do if you had a real assembler, what you'd type in, and they've nicely commented everything too. So we're going to enter this program, and the only change I'm going to make is in this line. It has a delay, a count delay. So obviously if you had no delay in it, you would just see all the numbers flickering and wouldn't be able to read anything. This one lets you see it count, but I'm going to slow this one. I'm going to increase this number a little bit so you can even see the lower digits count up. And the way to do it is you use the substitute memory, then you look in the first column and it wants to go to 2000, next, and then we have to enter the numbers, the opcodes, which in this case are 31C220. So 31, next, C2 next, 20 next, and the fun just goes on and on. Oops, I turned off the camera. Okay, if you really want me to, I can re-enter them again, but no, just saved you some time. So now that the program is entered, what do we do here? We say go, don't be an idiot, go, that's the entry point, and then we say exec, and that ain't working. So let's try that again. Well, it seems I typed in a wrong number. So let's try this again. Go, don't error me, go 2000 exec. And there you go. You can see this, the lowest digit is readable with the delay value given in the book. I mean, that was just flying by, but even though this is a lot slower, there you go, the 8085 in action. I found another program example, which is, the header says, using the 8155 and 8355 device output ports. So maybe, so I think it's just counting up a byte for each port and then outputting it. And this is probably a good time to discuss what I think that stuff is supposed to do. So since this only outputs stuff, I mean, I've looked at this. I was going to sit down and draw a schematic, but yeah, why? Anyway, if you look at this, we got a bunch of, we got what, 8, 16, 20 LEDs. Then we got 1, 2, 3, 4, 5. These are open collector buffers, 7407s. And each one of them has 6 buffers in it. So we got 5 times 6. So these can actually drive 30 LEDs. But we only have 20 of them. And I really don't know. I entered that program. Let's see if it's going to send bits to all of the output ports. We should see these things count over here. So, how did this go? Oh, okay. I entered the new program. So we hit go, 2000, and exec. Oh, there you go. So all they're doing is, we're basically seeing 2 8-bit ports being output, and they're both counting very quickly. Of course, I may want to modify this too and slow it down, but looking at the code, they don't have a delay in here. But let's see if I can figure out how to put a delay in here, because these are going too fast. Obviously, these are going too fast. I want to see the lowest bit blink. Okay, that wasn't as easy as I thought, because I was trying to push the counters of these on the stack, call the delay routine, and then pop that again, because the delay routine, I guess, steps on a whole bunch of registers. So instead of spending too much time on this, I will put in a final program to make up for my failure. Well, after that fail, I decided to enter the last demo program, which is kind of appropriate for the situation I'm in. I mean, I I could have spent inordinate amount of time in figuring out how to save the registers so they wouldn't get stomped on and all that, but it just wasn't really worth it. So here you go, we say go 2010 exec, and there you go. I should have put up like artifact and stuff like that, but the monitor ROM does not support the letter R. And again, I could spend time on bypassing that and writing my own display routine and all that, but because of the aforementioned reasons, I'm not going to do that, and we shall leave it at that. A nicely working 8085 program. So finally, I have a question for my illustrious viewership. What I was thinking of, okay, we made the LEDs blink and that was cool and everything, but it is defacing this dev system, this classic dev system. This was built, I mean, I don't know what all of this stuff means. You could change bits, you could... The problem is, I can figure out how these are wired, and we obviously saw that we can take the output ports, make the LEDs blink, and with a little help we can probably read the switches too. But we don't know what this was used for, and I'm not going to try to figure out what the code was they used to demonstrate this. It doesn't look like it has any inputs, so whatever this is was run entirely by a piece of code to teach input and output ports or whatever. However, what I am thinking of and what I am leaning towards is cleaning up the prototype area, i.e. removing all of this, and bringing it back as much as I can to the original way it looked. It will look original, and it would fit back into this beautiful box, because it doesn't right now. The switches and stuff stick out too far. So dear viewers, what do you think? Leave me a comment. Should I leave this stuff on here, or should I clean it up? Thanks for watching. A like would be appreciated. Subscribe, and we'll see you next time.